Our final section, Chapter 2, Basic Principles and Concepts, Parasite Systematics, Ecology and Evolution. Parasite Evolution. As we're going to be talking about in the next chapter, there has been association over the years, okay, when we look at time immemorial, that as parasites have evolved, so have their host. There's been this, one goes up, the next goes up, type of a race. As I've mentioned in a previous lecture, parasites have had to adapt and push the envelope of just how far they can, maximize the niche they're in without unduly damaging or killing the host, because the host dies, pretty good chance that lineage of that parasite dies with it. So we see this coevolution. As the host evolve, so as the parasite. Now we're going to see and touch on it here and talk about it in the next in a couple of chapters, that there is the chance that parasite evolution may have also pushed the host to keep evolving. No parasites, minimal adaptations, minimal evolving. Maximal stress from the parasite, maximal stress due to the presence of, the load of the parasite meant that the organism had to adapt, had to evolve. Somewhere along in those millions of years, this ability to switch host, to jump from host to host, somehow had to evolve. So the host had to evolve. Host had to evolve preference for certain food items, certain snails over others, things like that, to allow for these new colonizations by parasites into new hosts. Those new hosts had to become preferred food items for the next intermediate, for the definitive host. We've been able to go through and look at, using modern day, molecular techniques, looking at modern day parasites, be able to come up with systematics, approaches in drawing up cladistic trees, so we can not only study the evolution of the different lineages of certain parasites, but then be able to draw assumptions of the evolution of the lineages of the definitive host and see the interplay. So when we look at these studies and we can compare, we can see that there are going to be characters, adaptations, that are either shared or unique. If they're shared, they're common. These are plisomorphic. This is what's going to be in all of that lineage, that evolutionary lineage, even the offshoot species. The apomorphic are going to be the ones that are the characters or adaptations that are unique or are only in a few of those organisms. And then we can sit there and discuss in-group, out-group. In-group are the ones that have this character, this what adaptation we're looking at, we're studying. Out-group are what we're comparing to. They don't have it, so we're comparing to this group, these individual organisms, so that we can have. You can sit there and discuss, this. Oh, look, it's round. It's furry-ish. Well, aren't all things round and furry? No, this one's kind of roundish, but not. You have to have something to compare. In-group is what you want. You want to study, you want to discuss. Out-group is what you're using as a comparison. So when you go and you look at the cladastic trees, You can see here on the right, we have this cladistic tree of the different parasites that all come from this one lineage. They evolutionarily evolved. And we can see who came first, what was the common ancestors, and things like that. Well, over here on the left, we can also do a cladistic tree of different sharks and different skates and see how they relate to each other. What's the common ancestors? What's the common lineage? You know, what was the term used? The plesiomorphic and the apomorphic characteristics. And once we have the two trees, we can then take the data that we have collected of who's been infected with what parasitic load, and we can start drawing and determining that, you know, the Acanthoborythium parvicatium seems to have a definitive host, that is the Urobactis halaria. But Acanthoborythium putrescens seems to prefer Heterodontus francisii. So when you look at and you compare, and you can see the lineages, the oldest, the relatively newest species don't always line up. Turns out some of the oldest may prefer some of the newer, and vice versa. What we have been able to study and figure out is that parasites have influenced the evolution of other animals, specifically our reproduction. We look at reproduction in the animal kingdom. The female will choose the quote-unquote best of the males. Well, turns out parasitism, parasitic load, health based on parasitic load will impact whether or not a male is considered to be the best. So as the females are choosing, as I said, the females are choosing the best of the males. Let's talk peacocks. I like to use peacocks. Peacocks is a great example. Whether they're ecto or endo parasites are going to, either one, both, are going to influence the overall appearance of the plumage of the peacock. If it's an ectoparasite, there are different mites and things like that that are going to hinder the production of feathers. They're going to hinder the oil production. They're going to hinder the ability of the peacock to keep its feathers cleaned and groomed. Endoparasites are going to be sapping away at the nutrients so that the peacock is either going to be physically weaker, it's going to be sickly, thus it's going to affect its oil production. The lack of nutrients, the oil production is going to affect its ability to preen, keep its feathers looking good, because it has to spend more time trying to get nutrients, hunting for food. So compare that with a peacock that has a lower parasitic load, or its lineage, its genes have allowed it to be able to resist the parasitic load better. So it doesn't have to go and spend as much time hunting for food. Its plumage is still nice and preened because it's healthy and it's able to keep things clean, keep all the ectoparasites off of it, or minimal, keep it down to a minimal number. It just looks better. Female will pick the best plumage, which means the healthier male. The one that was sick because it couldn't resist, it was more susceptible to a parasitic load, whatever it was within its genes that meant it was more susceptible, die off with it. The male that had the higher resistance means it was less susceptible. Whatever whatever adaptations allowed it to be better off, get passed on. Same with us mammals, okay? Yes, us humans, we use vision. Ooh, she's cute, he's cute. We forget, though, that we mammals also smell, the pheromones, things like that. A nice, healthy animal, nice, healthy, means the parasitic load is either low or their resistance to the load is quite high because genetic predisposed to being able to handle the parasites means they're going to be healthy, means their pheromone production is going to be at their highest peak. Flip side, genetically predisposed to be susceptible to parasites means it's going to be a little weaker, it's going to be a little sickly, and its smell, the pheromone production, is not going to be quite there. Boom. Once again, whoever can handle the parasites is going to be the healthier. They're going to have the greater the chance of passing on their genes.